to that protocol, for example, like the port number, okay, port number, the checksum, okay. So those are pretty straightforward, right, and very important to that UDP protocol. We don't have any extra information to ensure any reliabilities in the for the communication, right? All right, so let's move on to that we finished UDP. Okay, so let's move on to the other protocol, right? Right, so the next part we're going to cover about reliable data transfer. So what does it mean? It means, all right, UDP is an unreliable data communication protocol. It means that when you transfer, you cannot be sure that your data arrive at the other end 100% consistent, right? Or 100% correctly, right? So in some scenario, it's good because it's provide a very fast communication, right? Ad hoc communicate, kind of, like ad hoc, right? But then in other cases, most of the cases, we need our data transfer to be arrived at the other end of the receiver 100% correct, right? Everything is persists, right? Consistent, right? So the idea is we have to build up some things that is reliable, okay, right? But the thing here, as you may realize, the communication media, right? For example, like the cable, okay, the wireless, okay, the wire cable, right? All those, for example, all the fiber, even on fiber, okay, it's not a reliable channel, okay, right? So the infrastructure is unreliable by default, okay. The infrastructure is unreliable. It does not, the infrastructure does not ensure anything. I mean, the physical infrastructure is not it's not like reliable. It's an unreliable environment, right? And your mission is now, our mission is to build something reliable, okay, on top of something unreliable, okay. That is the idea of building up the reliable data transfer, aka that is the TCP protocol, right? But we start as a very simple one, all right, very simple, okay, right? Based on some assumption, okay. So let's talk about the reliable data transfer protocol, right? So here is say what, okay, if we have a like a sender here and we have a receiver here, okay, and if we have a reliable channel, then nothing needs to be discussed here, okay? Everything's will be normal because reliable channel already provide for us, so we don't need to do anything, okay. That's it, right? So very simple, right? Okay, right. So but basically, right, in real life it does not looks like that. There is no something called reliable channel. There is no reliable infrastructure. But actually, we have unreliable infrastructure. Okay, channels here. Okay, and we need to, okay, here is the unreliable channel. Okay, so you see that the network is unreliable. Okay, so our job is to do what? Our job is to here, right, to implement, okay, the transport layer. Okay, so the network below is unreliable. We are in the transport layer, provide a service for the application layer. Okay, right. So we have the unreliable channel below us. Okay, so now we have to transfer it to something reliable. Okay, so that we can provide a reliable service to the application layer. So that is the idea. Huh? Right. So it's very complex. Okay, so building a reliable data transfer based on something unreliable, it's very complex for sure. Okay, right. So for example, like we need to care about some loss. Okay, some loss during data communication. Okay, we have some corrupt. It means the data received, but it's wrong. Okay, right. And real data, it means the data we receive is not in order. Okay, so as for example, like we send 1 2 3 4, okay, and we receive like 2 1 3 4, for example, right? Okay. And also by default, the sender and the receiver do not know about the state of each other. Okay, right? We don't know because like by default, okay, we cannot know the status inside the sender or inside the receiver. The other do not know. Okay, the other guys does not know about us. Okay, right. So we need to communicate those status. Okay, to make sure that we agree on the transmission. Because, for example, all right, when the sender send data and the receiver receives some data, okay, right, and the receiver check the data and properly the data is corrupted. Okay, right. So that is the data is corrupted is an internal state of the receiver. Okay, right. And the sender by default it does not know about that. Right. So we need to transfer, or we need to also indicate that status to the sender, so that the sender know exactly what happens with the data arrive to this arrive at the like receiver. Okay, right. So we need to know all those input, right, to make our communication become reliable. Okay, right. So you can imagine, like for example, like when you talk to your friends, okay, right, and if your friend cannot hear you, he or she need to say nói gì vậy, nói lại đi ha. For example, like please repeat. Okay, so that is please repeat is a kind of like indicator or state or status of your friends. Okay, that he or she cannot hear the conversation, right? And he or she needs you to repeat, okay, the sentence or the conversation again. Okay, right? Because we need to do such kind of things. Okay, right. Rồi. Okay. Or you can imagine like when your friends, okay, sorry, when your father, when your parents ask you to do something, okay, you need to reply to them. For example, bố mẹ con nghe rồi ha, okay, okay, right. Ví dụ như bố mẹ gọi, for example là An ơi xuống ăn cơm, okay, right. So you need to reply, con xuống đây. For example, you need to, for example, like ping back, okay, right, acknowledge with your parents so that you already received the information, okay, right. Okay. So we define some things. We define some things. Like when we build up the reliable data. Okay, I will not cover all of the version of the RDT. RDT stands for Reliable Data Transfer Protocol. Okay, so I will not cover, like all of the version. Right? Just one or two. Okay, and then you read on and like. Pick it up by yourself. The latest version. The latest version is, I believe that is the 3.1. Okay, that is the foundation for building up the TCP protocol. Okay, right. So let we define some of the interfaces and terminologies in this RDT. Right. So you can see that we have the application here, application layer here. Okay, right. And it is application layer on the receiver side, and on the receiver, on the sender side and the receiver side, we have two interface or protocol. Okay, right? RDT send. RDT send. What does it mean? When let's say, for example, when you write an application, you want to call the RDT send. What does it mean? It means that you send data and you you want to make sure that the data will arrive at the other end correctly. So that is the idea of the RDT send. Okay, right? And in the transport, this is the transport layer. Okay, right? We have to call UDT send. What does it mean? Unreliable data transfer. Because why? Because the service in the network only provide us an unreliable data transfer. Okay, right? So we have to transform from UDT send to RDT send. See, and this is the job of this implementation. Okay, right? Similar on the other side. Okay, right? On the other side. Okay, right? We need to receive a reliable data transfer, even though we receive here is unreliable, but like we need to make sure that we receive data, everything is correctly, right? And so that we can deliver the data to the application, right? Okay, right. Those are the four interface. I mean, basic four interface that we need to build up. Okay, the IT. Okay, so this is just abstract protocol. Okay, right. It's not actually exists in real life. Okay, right. The fully implementation of this one is actually the TCP protocol. Right. Okay, right. And we also make use of, you know, like state transition, okay, state machine, okay. Or I'm not so sure that you study in during mathematics. It's automata, huh? Okay, automata. So it's the code, for example, like finite state machine. It means, for example, like if we are in the state one, okay, and we need some event. We need some event, okay, and the event is, you know, like match the transform of the state. Okay, for example, like here, when this event happens, then we're going to perform some action, okay, and then we're going to change state. Okay, we're going to switch state, okay, change state. Okay, right. So event happens, we perform action, and then we change the state. Okay, right. So that is the ideas of the finite state machine. Right. Okay. Okay. So let's start with the 1.0. Okay, right. So the 1.0 is the network underlying channel is perfectly reliable. It's been everything is reliable. Okay. There is no bit error. There is no lost packet. Okay. So what is the protocol look like? The protocol is look like this. Okay. Right. So on the you know, like on the sender side, okay, we're going to wait for the call from above, wait from send from above, well, wait from, you know, like send reliable data center, right? So upon receive the RET send data, yeah, yeah, see here we have state here, huh? Okay, right? And when we receive this event, okay, RET send, okay, right? And then what is the action? What is the action? Sorry, what is the action? Okay, right. So we will receive an event send request for send data from the application layer. We're going to what are the action? The action we're going to create the packets or MAC data. What does it mean? It means the application will give us some data to send. Okay, so we need to break it into to datagrams, for example. Okay, right? Datagrams, okay, right? And then we're going to call what? UDT send. UDT send. Okay, this is one of the interface on the sender side. UDT send unreliable, but actually in this version one, the you know, like the underlying channel or network is reliable. Okay, right. How about on the receiver side? On the receiver side, we wait a call from above, right? Below, sorry, from below, right? And we receive data. We receive the packets. Sorry, we receive the packets. For example, like let's say UDP packets. Okay, example, right? And then we're going to extract that packets. It means we remove the header. We remove the headers, and then we also, you know, like combine all those packets into the original message or data, and then we're going to deliver it to the application or the upper layer. Okay, right. So for the version 1.1.0, it's very simple because, you know, like we assume that the network is reliable. Okay, right. And this is on theory. This is in theory only because there's no such thing happens in real life. Okay, there's no so-called reliable channel. Okay, reliable network. Okay, in real life. I don't. Yeah, something's happened with my network this morning. Question regarding the version 1.0. Okay, so we're going to move on, you know, like version 2.0. Okay, right. And the version 1.0, 2.0 is you know, like introduced, you know, like the first you know, like unreliable parameter. Okay, and it's my flip bits. Flip bits in the packet. What does it mean? It means the original packet, the bit is one. Okay, but when it's sent, okay, and the receiver receives 0, so that is the idea of flip bits. Okay, right. That is the idea of flip bits. So So how do we do that? Okay, how do we deal with that? Okay, right. We're going to use checksum. Okay, the checksum that is I already mentioned to you in the last lecture. So we will introduce checksum. Okay, so checksum is meant to detect the bit error. And let's say, for example, like if we can, let's say if there is one bit error in the in the data received, we just simply flip it again. Okay, flip it again. Okay, right. The error is like 1 to 0. So now we simply flip again. Okay, from 0 to 1. If we can detect the bit error. Okay, right. And how to recover from error? The one of the mechanics that I just mentioned to you. How about that? We can simply retransmit, for example. Okay, right. Right. Yeah. So we're going to send acknowledgement. Okay, to indicate the for example, if your data received correctly, you're going to send some acknowledgement. So yes, I hear you clearly. For example, okay, yes, I received the data correctly. Right. It will explicitly tell the sender that packet received okay. Okay, so that is the idea of ACK, right? Acknowledgement. Right. And negative acknowledgement, NAK. What does it mean? It means that you will say explicitly to the sender. I cannot hear you clearly. Okay, tôi nghe gì đó. Okay, I cannot hear you. Right, please repeat it. Right. So similar in network, we can send NAK. Okay, so explicitly tell the sender that packet has error. And retransmit, we retransmit. Right. And we have the terminology stop and wait. So what means stop and wait? It means and when you send package, we're going to stop there and wait for a response. Okay. It's very similar like in walkie-talkie or radio. Okay. So one side talk. Okay. Right. Hello, bạn nghe không? And then you stop, release the speak button. Okay. And then the other side. Hello, and press the big speak button. And hello, nghe rõ. Okay. Right. And you release the button, for example. Okay, so stop and wait, stop and wait. Okay, so radio talking over the radio or walkie-talkie it's like that. Okay, using stop and wait. Okay, you cannot like you don't want to talk multiple times or talk at the same time. See, if you use your cell phone, mình dùng điện thoại di động, okay, right, and then it's like full duplex. It means like both of you guys speak at the same time. But for example, like walkie-talkie, okay, right, stop and wait. You speak, you finish your speaking, you stop and you listen. Okay, right. Let's talk about the 2.0 version 2.0. Okay, right. So very similar. Okay, right. So I have wait from above. So when I receive, okay, sorry, when I send data, okay, right? When I receive an action from above, that is send, okay, right? And I will map data and I send. Very straightforward. Everything, every single time, we need to do this kind of thing, and we're going to stop and wait, okay, right? So we're going to change this to this state, okay? We are wait for the ACK or NAK, okay? Right. Okay, right. And then when we so in this state, when we wait for ACK and NAK, and if we receive some data from the receiver, okay, right? The receiver send back some feedback for us, okay, right? And if this packet that we just received is an NAK, okay, negative acknowledgement, then we're going to try to resend the packets. Okay, we resend it. Okay, we resend the packets. Okay. Otherwise, if the packet that we just received, okay, we just received a packet and the packet is an ACK, it means everything's arrived successfully. Okay, correct, 100%. Okay, then we simply change this to this state. Okay, we don't need to do any action. Okay, we don't do any action because no point. How about on the other, on the receiver side? On the receiver side, very similar. Okay, if we receive the packets and if the packet is corrupt, we send NAK. Okay, right? And again, if we receive packet, it's not error, no error in it. Okay, so we're going to extract the data. We're going to deliver data, and we also need to send the ACK. Send the ACK. Okay, acknowledge that the data arrived correctly. Okay. Move on. Right. It's the explanation that I already explained to you. Okay, right. So Okay, I'm going to go fast. Okay, right. But there are some critical problems with the 2.0 because why? In 2.0 we assume that okay, the data packets is sometimes corrupt. Okay, but we didn't have this situation. We didn't consider this situation. Okay, so when we send the ACK and NAK back to the sender, there are chances that the ACK or NAK will be corrupted. Okay, right? Because NAK or CAK is just also data. Okay, right. So there's chance. So we don't need to. We cannot deal. We didn't deal with that yet. Right. Okay. Right. So simply we can just retransmit because why? Let's say if the so when the NAK or the ACK is corrupted, what happens? What happened is, like the sender doesn't know what happened at the receiver. Mình nói bạn mình nghe ha. Alo, em nghe rõ không? Cái xong im lặng không nghe nói các bạn gì đó, thì sao mình hoang mang không? Okay, yeah, you're going to be confused, very confusing, right? Right. Thì sao? Yeah, you can say again. Em nghe nữa không? Nói nữa không? Lặp lại không? Okay, right. So it means, like duplicate. Okay, right. If we try to repeat, it's duplicate. Okay, right. And for sure example like so usually when that thing happens, for example, anh nghe rõ không? Okay, and you try to retransmit again, anh nghe rõ không? Okay, so couple times after that, okay, we can simply just hang up. Right. So, but how about in network, in transport, okay, right? So we have to deal with the duplicate. Okay, right. Okay, we handle duplicate. So how do we do that? Okay, right. The sender will retransmit the current packet if the ACK or NAK corrupt. Okay. For example, like if we're going to maintain a timeout. For example, like timeout. After it send a packet, it will maintain a timeout, right? And it will like retransmit after time is out. Okay, right? Okay, right. And also we're going to add the sequence number to each packet. It means that we're going to add, like the number. And if we receive two packets, we have the same number. It means it's duplicate. Okay, right? And we're going to discard the duplicated message. Okay, right. Here is the action, right? So also send, okay, and we're going to send, okay, and remember we send with checksum, okay, right? And then the receiver, sender, okay, right? So when the sender receive a packet and it's not corrupt, and it's also in ACK packets, so we do nothing and we wait for verb. Okay, right? Wait for verb. And assume here we have two sequence 0 and 1. Okay, it means we're going to send 0 packets out. Okay, and then we're going to, after we finish sending 0, we're going to send 1. Okay, that is the idea. We only dealing with sending 2 message in this example. Okay, right. Right, wait from 1 from both. It means wait for another call. Okay, for another call for message 1. Okay, this is message 0. This is the 2 state for the message 0. These are the 2 states for package 1. Okay, right. Right, so we're going to wait for code from above, okay, and wait for ACK. Those is similar, right? We're going to send, and this is ACK. Then we're going to not corrupt, and then we just simply sending the next batch, okay, right? So we send 0 and 1, okay. Finish 0 and 1. We're going to go back, okay, and next batch, okay, next batch 0 and 1, okay, next batch 0 and 1. In real life, actually, we continue that number, okay, 0 and 1, okay, 2, 3, okay, and 4, 5, 6, 7, so on. Okay, but in this example, we just like repeat the batch, okay, 0 and 1. Right, and here's the situation when we receive the packet and the packet is corrupt. Okay, right, or the packet, this is or the packet is a not acknowledgement, okay, negative acknowledgement. Then we're going to resend. Okay, this is retransmit. Okay, resend. Or we call retransmit. Okay, right. So what happened? Retransmit, and we need to wait also. Okay, right. Right. So NAK1, for example, similar. Okay, we recheck it as well. Right. And how about the receiver? The receiver side, we also wait for 0 from below. We're going to wait for packet 0 from the like from the network layer to deliver to us. Okay, so what happened when we receive a packet and packet is not corrupt, okay, and it has the sequence number 0, it means that we are waiting for 0. We are waiting for 0 and we receive 0, right? So we're going to deliver it, okay, and send back the ACK. Okay, similar, we wait for 1, okay, right, and we receive packets. It's not corrupt and it's the packet 1, so we also like deliver the data. Okay. How about in terms of when we receive the corrupt one here? When we receive the packets, okay, it is corrupt and it is corrupt, okay, and then we're going to send the NAK, okay, right. Similar for 1, okay, right. We receive the packets, okay, sorry, still 0, okay, it's not corrupt, okay, and it has sequence number, so make ACK, pretty straightforward, right. Similar for 1, right. So this is the receiver, right. All right. So we have, like sequence number active packet to sequence number insert. Okay, right. Okay, so as well, you see. So you see that with this scenario, okay, when we're dealing with just simply out of order or duplicate message, you see that we have, like twice as many steps. For example, like before we only have 1 step. Okay. So now we have like 4 steps. We have 4 steps at the sender. We have like 2 steps at the receiver. Okay, and so on. Okay, so it becomes like the protocol become pretty complex already. And let's say if we have like if we have like more than 2 sequence, for example, like we have 0 and 1, right? But let's say we have like 0 and 1, 2, 3, 4, 5, 6, okay, and then we have like more state, we also double, like the effort, okay, to making the protocol enable, making the protocol like exist. Right. And we have 2.2, okay, right. So 2.2 is like it's just like a mechanics, okay, right. What is a mechanic? An NAK free protocol. What does it mean? It means that in this protocol we only use ACK, we do not use NAK, okay, right. No, we don't use NAK. All right. So how to deal with that? Like, so instead of like sending NAK here, instead of sending the negative acknowledgement, we're going to send ACK for the last packet received. Okay. What does it mean? You can imagine the idea is something like this. Okay, right. Sorry. Yeah. Okay, we have the sender here and we have receiver here. Okay, right. So we're going to send packet 0. Okay, right. And then we go for example, like here. ACK 0, ACK 0, let's say, okay, right? And then let's say we send 1, somehow it's corrupted, okay, right? Somehow it's corrupted. So instead of sending NAK1, okay, right? No, we don't send NAK1, but we're going to send ACK 0 again. Okay, right? We're going to send ACK 0 again, right? So the receiver send ACK for last packet received, okay. Right. So what happened when this one? The sender received ACK 0 again. So it means that there's some problem with ACK. Sorry, there's some problem with the packet 1 I just received. So I need to dealing with this problem. Thì vừa gửi packet trước đó. Okay. Cái packet có vấn đề. Okay. Right. Cho nên cái thằng nhận nó mới nhận được cái 0 thôi. Okay. Right. We need to dealing with something with the packet 1. Okay. So that is the whole ideas of like adopt like ACK to resolve to dealing with NAK, okay, right? Instead of like use the NAK directly, so we use the technique ACK, okay, to transfer the ideas of NAK. Okay, right. And actually TCP use this one, okay. TCP nó dùng cơ chế này okay, right. And we go into detail when we talk about TCP, okay, right. All right. So here is basically again it's just another state machine talking about the one that I just mentioned. Okay, so please read it by yourself, huh? Okay, right? See? Okay. Right. And in 3.0, okay, we're going to have the channel with the errors and loss, okay, error and loss as well, okay, right. So for example, like we also lose ACK, we also lose data, okay, right, and a lot of help, okay, right. So we check some we have sequence ACK not quite enough, okay, right. So these are the consumption, right. So how do we handle in this kind of things, okay, right. So approach is we're going to retransmit if no ACK received on this side. So we're going to introduce because ACK lost, okay, because stop and wait. So we wait. You are waiting for the ACK, but the ACK already lost. Okay, so how to deal with that? Timeout, the one that I just mentioned to you in the in those previous slides. Okay, right. So you send out a packet, right, and waiting for ACK, all right, and you start the timer, okay, right. And if you cannot receive ACK within within a time frame, so you're going to start just retransmit right away after its timeout. Okay, right. So that is the idea. Because why? ACK has the probability of loss. Okay, cái ACK có thể bị lost. Okay, chúng ta đâu có đợi mãi được, huh? Okay, we cannot wait forever. Right. So you can see that if you retransmit, but the ACK is lost. Okay, the packets arrive correctly, but the ACK is lost, right? So there will be duplicate. Okay, but the sequence number that we introduced previously can handle the duplicate, right? And also the receiver must specify the sequence number of the packet being ACK. For example, I need to specify this is the ACK for packet 0, and this is the ACK for packet 1. This is the packet ACK for packet 2. Okay, so on. Okay, that's it. Okay. Okay, countdown timer. Okay, so here is the action of the TTV sender. Okay, 3.0 sender. Right. So again, it's very similar like previously. It's just we're going to have a stack timer here. We're going to have a stack timer here. Okay. We stack timer. Okay. And then after we receive the ACK, okay, we're going to stop the timer. Okay. Stop timer for that ACK packet. Okay. Right. For example, we send 0 out. We send packet 0 out. And then we want to wait what? Wait for ACK 0. Okay, right. And then and when you send the packet out, okay, you stack the timer. We stack the timer. You stack the timer here, okay, right? You stack the timer here. You start the timer here, right? And when you finish the ACK, you need to stop it, okay? Giống như mình để cái báo thức đấy đúng không? Được chưa? Mình dậy rồi thì mình tắt đi chứ đúng không? Okay, right. Example. So similar, start timer, stop timer. Okay, and for example, if there is a timeout, if there's a timeout, then what happened? You're going to send timeout thì mình làm gì? Mình phải send nó, we send packet again, and start timer as well. So it's remember, whenever you send out a packet, you must what? You must start the timer, right? Because you are waiting for the ACK acknowledgement for that packet, right? So you need to start the timer. So it's the whole thing's repeated, right? As well. Right. So I'm going to skip this one. Right. Okay, here an example, okay, see, right? So I send packet 0, I receive packet ACK 0 as the one that I just mentioned to you earlier. There's no loss. Okay, here's the things. Okay, right. So receive 0, 0, 1, 1. Okay, 0, 0. Okay, everything is right normally. Okay, how about this one? I send packet 0, I send back ACK 0, I send packet 1, it's lost. Okay, right, and it's timeout. Okay, so I'm going to send packet 1 again, yeah, right, and then ACK 1. Okay, so packet lost. Okay, lost. Right. Any question up to this point? Ta có hỏi gì tới đây không? Okay. For example, let's say if I go too fast and a little bit confusing, right? But just consume it, okay, right? And read the material, read the book, okay, right? There, yeah, you can understand more clearly about this one. I think here, remember, timeout. Yeah, right. For example, when the time is up, okay, it's 0, okay, it means that we cannot wait anymore, okay, we cannot wait for the ACK anymore. We're going to resend the packet, right? In the case of scenario is ACK is lost, okay, so what happens? So we need to send packet 0, okay, right? Pick one. Packet ACK is one is lost, okay, right, okay, see, right? Packet 0 send out, ACK receive 0, so everything's fine, okay, right? Packet 1 send out, ACK 1 send back, lost. All right, so what happens? Timeout, okay, we are timeout. Because we already have timeout, so we simply resend packet 1, okay, resend packet 1, okay, right? And you see that, we detect duplicated here because we receive packet 1 here, we receive another packet 1 here, so we need to discard one of them. For example, let us say we're going to remove this one, so upon receiving this one, we need to send also ACK1, okay, right, 0 and ACK 0 and so on. Right. There is a premature timeout and delay ACK. What does it mean? Here I send packet 0, packet ACK 0, then nothing really happens. Okay, right? When I send packet 1, there is a chance that the ACK 1 receive, like access the timeout. What happened? What happened is that, like before I receive ACK 1, I already resend packet 1. So it's very similar like this one. Okay, we receive duplicate message. Okay, right? And we receive duplicate ACK. Okay, but it's okay. Okay, right? Because after we receive ACK1 here, we also like send another 0 packets for the next batch. Ta gọi thêm một cái message khác của cái next batch nào ha. Okay, so everything is fine. Okay, right. And if we receive a duplicate ACK here, we just ignore it. Okay, we don't do anything. Okay. Right. Any question? Ta hỏi gì không? Any question here? Right. So you have any question? Then move on. Here it's just some utilization. Okay. Right. So you can read it on by yourself. Okay. Okay. Right. So here is like the explanation of the stop and wait operation. Right. So we have here we send a packets. Okay. Right. We send a packets. Okay. And then we receive ACK. Okay. Right. This is one round trip time. Okay. One round trip time. Right. R divided by T. What is that? Sorry, L divided by R. Okay, what is that? L is the length of the or the size of data, or R is the transmission rate. So it is the transmission time, okay, for the packet. Okay, so this is the R. This one is L divided by R. Okay, right? The transmission times of the packet plus the round trip time. Okay, right. So this is the so when the first packet transmit and the ACKs arrive, ideally, okay, ideally the total time for that is round trip time plus transmission time. Okay, L divided by R. Okay. Right. So what is the start and wait operation utilization? You can see that it's just very small, because we send out a packet and then we need to stop here. So you see that from here to here, the time is waste. Okay, mình đợi mà cho nên sao? Resort is waste. Resort is wasted. Right. So that's the reason why the utilization is very small. Okay, right. Right, so how do we deal with these things? We need to, let's say, for example, like increase, like queuing and stuff, okay? Transfer multiple packets at the same time, stuff like that, okay? Right. So we're going to introduce the pipeline protocol, okay? Pipeline protocol. What is that mean? What does that mean? It means that we're going to transfer or send, like a lot of packets at the same time. Okay. So you can see here is stop and wait. You can see that stop and wait, right? So this is California, this is New York, let's say, for example, right? And then we send a packet, one packet. We need to wait for so long to receive the ACK, okay? And then we can send next packet. Yeah. Nếu như mình đua xe đúng không? Đua xe tính giờ thì làm sao? Cho xe chạy đúng không? Cho xe chạy. Xe chạy xong rồi cho quay trở về, đúng không? Cho xe thứ hai chạy tiếp, đúng không? Okay. Right. So that is like stop and wait. Okay. Mình ta thể đua tức là sao? Dồn ra 10 xe chạy cùng lúc, cái rồi xong rồi quay về. Okay. Right. So it also saves some time. Okay. Right. Increase the utilization. Okay. Right. So here is the pipeline. So what is the pipeline mean? We're going to send a lot of packets. Okay. And then we're going to ACK a lot as well. Okay. Right. So what is the requirement for this one? The range of sequence number must be increased. So previously, stop and wait. We use one packet, okay, 1 packet, 2 packets at the same time. Here we're going to increase that to, a very large number, right? And we're going to buffering at the sender or receiver. What does it mean? It means that the thing here is when you send like 10 packets, okay, right. The receiver will receive those packets, but maybe not in order. So they cannot deliver the packets right away, right? So they need to buffer, okay, temporarily store the packets at the receiver. And then after it receives, like fully 10 packets, it will reconstruct, okay? Okay. To increase the utilization, you can see here, for example, right? We, we have time here. The time spent is still round trip time plus L divided by R. You see? Here. Round trip time. Sorry. L divided by R. Okay. And this is like one round trip time. Okay. Right. See? Right. But in this scenario, we already send 3 packets rather than just 1 packet. Okay. So you can see the utilization increased by 3 times. Okay. Right. And this is the pipeline of 3 packets. Okay. Cái pipeline là 3 packet cùng lúc. Okay. Right. So it will increase the utilization by 3 times. Okay. So it's also very good. Okay. Right. Then we're going to have an idea called go back end. Right. So what is the go back end means? Right. What is the go back end mean? Go back end mean we have a window size. Okay. Window size. Okay. Window size. Okay, sorry. So we have a window size. What does it mean, window size? It means it's kind of, can imagine like a maximum numbers of packets that we receive. Here in this scenario is the size is n. Okay, right? And we're going to keep track the number of what? Send base against next sequence number. What does it mean? The green one. It means it's already ACK. These packets in the Windows, if these packets are already ACK, so we don't care anymore. Okay. The current window size is the one that is sent. Include the one that packet that is sent but not yet ACK and usable, not yet sent. For example, like let's say assume that we have like how many packets here? Let's just assume that 10 packets. Okay, assume packets here. Okay, window size is 10. Okay, I already sent and already acknowledged. Sorry, I already sent but not acknowledged. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I already sent but didn't receive ACK for a packet. So I'm waiting for these packets to be ACK, to be acknowledged. Okay. Okay, so this is 16, okay, 16 packets. Okay, right. Okay, not usable. What does it mean? Okay, we don't care we only care about 16 packets that I'm working on. Okay, right? For packet, let's say 17. Okay, 17. Okay, I don't care yet. I do not care yet. Okay, right. So that is the idea. Right? So that is the Windows side. So what is the go backend? Go backend means, you know, like we're going to introduce something called cumulative ACK. What does it mean? For example, like when I send back an ACK, let's say 1 to 8, okay, 1 to 8, okay. Let's say when I'm waiting for ACK of these OA packets, okay, right? And then I receive an ACK packet, and that ACK mentioned that is 4. ACK I receive is 4, ACK 4. Tôi nhận được cái ACK. Tôi có 8 packet. I have 8 packets that in line for waiting ACK, okay? And I receive ACK 4. Okay, right. So what does it mean? It means that the sender already received up to packet number 4. Okay, right. So it already received 1, 2, 3, 4. Okay, right. So it means that this one is already finished. I already received the sender, the receiver received up to 4. Okay, right. So I'm going to move up the windows. Okay, right. And this one is become green. Okay, become green. ACK already. Right. And the ACK is this one. Okay, 5, 6, 7, 8. Okay, so that is called cumulative ACK. Okay, tức là ACK cho một loạt luôn. It means that ACK number 4. It means that I already received 1, 2, 3, 4. Hiểu không? Thì mình nói là bạn mình gọi là mày đọc mày nhận được tài liệu 1, 2, 3, 4 chưa? Mày nhận được tài liệu 1, 2, 3, 4 chưa? Thì anh kia nói là không, bạn kia trả lời là mày nhận là tài liệu 1 chưa, mày nhận là tài liệu 2 chưa, mày nhận là tài liệu 3 chưa, mày nhận từ 4 chưa, ví dụ vậy ha. Okay, thì bên kia trả lời là tao đã nhận tới tài liệu 4 rồi ha. Okay, it means that I implicitly imply that okay, the receiver already received 1, 2, 3, 4. Okay, and it's expecting number 5. Okay. Okay, see, so it's move window forward to beginning n+1. Okay, right. If ACK received n, it means that it is already up to okay, up to including sequence n. Remember this one. Okay, timeout. Retransmit packet n and O packet. What does it mean? So when you retransmit packet, if we have timeout n, okay, right? If we receive a timeout n here. For example, I receive timeout n, it means that I will retransmit all the packets n and all higher sequence number in the window. For example, like if the packets are 1, 2, 3, 4, 5. Okay, right? Already ACK and timeout 6, for example. Okay, it means that I need to retransmit 6, 7, 8. So when I retransmit, I do not retransmit packet individually, but I retransmit the whole batch. Okay, from the current point to the very end of the you know, like the list. Okay, for example, like here we have 60. Here, let's say we have 8 in the batch. Okay, right? Actually, let's say here. Okay, right. So let's say, for example, I have timeout at number 9. Okay, number 9. Okay, right. So I'm going to retransmit from number 9 up to this point. Okay, 9, 10, 1, 2, 3, 4, 14. Okay, 14. Okay, 14. Okay, so I'm going to receive up to So last time the packet should be size is 14. Sorry about that. Okay, right. So for example, if I receive timeout 9, I already sent out packet number 9. Okay, all right, and now it's timeout. So I'm going to retransmit the whole thing. Okay, 9, 10, 11, 12, 13, 14. Right, not just number 9. Okay, I will resend the whole batch. Any question here? Right. It's just some initial, you know, like terminologies and techniques that we're going to use apply for TCP. Right. Học tiếng đang vậy hàng. Okay. Right. So let's move on. Right. This is the go back end in sequence. Right. In action. Sorry. Okay. Right. So for example, let's see. the packet, no, I send out 0, 1, 2, 3. Okay, I receive packet 2 is lost. Okay, right, and it will receive packet 0 and 1. Okay, right, 0 and 1. It receive packet 3, but packet 3 is out of order because the receiver did not receive packet 2, yes, okay, and it received packet 3, so it will resend ACK1. And why is that? It's because that it wants to indicate the sender that I receive up to 1 already. Okay, so you need to do something with that. Okay, so the sender will receive packet 4. Okay, it will resend ACK once again. Okay, right. Okay, it receives packet 5, resend again. It does not accept out of order packets. Right? Okay, ignore duplicate. These all we ignore duplicate. Ignore duplicate. Right. Okay, right. So and now packet 2 is timeout. Packet 2 timeout. Packet 2 timeout. Okay. So now it will send out what? It will send out. Can you guess? Okay, it will send out 2, 3, 4. Okay, right. 2, 3, 4, 5. Okay, it will send out 2, 3, 4, 5 at the same time. Okay, right. So this is go back end. When it's sent, even though even though it duplicate, okay, it will be duplicate packet packet 4, okay, packet 5, okay, right, but it's go back end. We need to implement like this, okay, to reduce, okay, right, the like the complexity of the machine. Okay, that is go back end. How about selective repeat? Selective repeat is like different from go back end. For example, like we need to transmit the packets, any packets. Okay, we're going to indicate that only packets. See, for example, so we're going to have like the window size now is a little bit not consistent like the go back end. For example, like we have ACK. Okay, we have ACK. Okay, but we only have the ACK here. An ACK here. All right, different from go back end. Okay, go back end you can see here. All of the ACK we don't care. Okay, within our Windows side we only contain the UNACK and the unsend. Okay, unsend. Okay, not yet send. Okay, right. But in selective repeat, because like because we going to send ACK for individual packet. Okay, so there is a chance that we already send 1, 2, 3, 4, 5, 6, 7, 8. We already send out 8 packets, but we only receive ACK for 3, 4, 6, 7. 3, 4, 6, 7. 1, 2, 5, and 8. We didn't receive it yet. Okay, right. So we have to keep track. Okay, and when we retransmit, we just retransmit those packets. In case of timeout, okay, we just send out the packets that individual packet that necessary to retransmit. Okay, we don't retransmit the whole bunch of packets in line. Okay, right. Okay, right. So okay, right. Okay, we're going to resend packet n. Okay, in terms of timeout n, we're going to receive only packet n. Okay, we do not receive packet n and all of the packets in higher order. Remember that. That is the major difference between the go back n and the selective repeat. Okay, right. Right. As you can see, 1, 0. Okay, packet 3. Wait. Right. So I will receive ACK of 1, 1, 2. Sorry, 0, 1, and 3. Okay, right. It will send out 4. It will send out 5. Okay, right. ACK3 arrive. Okay, right. Packet 2 timeout. We're going to send out packet 2 only. Okay, right. Not 3, 4, 5 line in the go back end. Right. Right. So can you guys tell me which protocol is which protocol is in these two protocols? Okay, compare between go back end and selective repeat. Which one is so-called more effective than the other in terms of utilization? Which one is more effective in terms of utilization? Okay. in terms of effectiveness, okay, right, in terms of effectiveness, which one is more effective? Rồi, ai trả lời được không? Hai cái protocol này thì protocol nào nó sẽ effective hơn ha? Okay. Hiệu năng nó cao hơn, phải say phải mà utilization ha. Okay. Which one? Nghe không hiểu gì hết hả? Okay. Trọng Tấn. Trọng Tấn. Okay, hello Tấn. You hear Tấn? Which one is so-called? You see that is more, you know, like effective in terms of, let's say, resource consumption. Bạn thấy trong cái protocol này, Tấn? Hello Tấn. Tấn is here, Tấn.
Yes, teacher.
Okay, right. So in this in these two action in these two mechanics, okay, right? Which one do you think that is more effective? Cái nào em thấy là effective hơn? Go back and send everything back, everything again. Okay, right? Selective, send only one that necessary to retransmit. Right. Thằng nào effective hơn? Một thằng là send toàn bộ lại đúng không? Một thằng chỉ send những cái nào cần send lại thôi. Okay, so thằng nào sẽ effective hơn?
Yes, selective.
Okay, selective. Okay, because why? So you see that, for example, in case of you know, like resend, it's only resend packet 2. But in this one, you see retransmit, time out. We're going to resend with everything. Okay, right? Not everything. It means that retransmit from the current packets to all the packets in the Windows. Okay. I mean, which one is more? How can I say? Which one is more complex between the two? Okay, which one is more complex? Right. Hello Mẫn, hôm nay có micro Mẫn, hello. Hello Mẫn. You hear Mẫn? Chạy đâu rồi hả? Mà hello Hồng Anh, hello Hồng Anh. You hear Hồng Anh?
Yes, teacher.
Yeah. So between selective repeat and go back and which one you think is more complex to implement in terms of, you know, implementation? Cái nào dễ làm hơn, cái nào khó làm hơn? Cái nào phức tạp hơn? Which one is more complex? Phức tạp hơn? Hai cái mechanic này. Which one is more complex? Which one is more complex? Which one? Just make a guess. Em guess thôi, không phải là đúng không? Okay, make a guess. Just make a guess and telling me that which one is more complex. Hello. Đánh đại đi, gì đó sai thôi là anh gì? Okay, right. Which one is more complex? Right. Between the two. Right. Anh đâu rồi? Đánh đại đi, có gì đâu, sai thôi, đâu gì đâu. Ngại gì? Hello. You hear anh? Yes, sister trong đâu mất rồi? Hello. What? Hồng Anh, hello.
Yes, I'm here. I think.
Just give me multiple choice, huh? Okay, right, multiple choice. Okay, selective repeat or go back end. Right. Which one? Multiple choice thôi. Rồi, em được chọn một trong hai. Rồi, chọn cái nào?
Sender.
Selective repeat. No. We have selective repeat and go back end. Right. Which one is more complex? So we have here.
I think selective repeat.
Okay, right. So I'm asking which one is more complex. Okay, go back end or selective repeat. Okay, agree. Okay, right. Selective repeat is selective repeat is more complex. Okay, more difficult to implement. Because you see that we have to deal with individual packets. Okay, we have to keep track of like all the individual ACK here. Okay, right. And you can simply just look at the windows, keeping track of the windows. See here, right? All the yellow colors and the green colors and the blue colors are mixed up. Right? There is no, let's say, area. Okay, there's no separation for them. Okay? They just mixed up all together. Right? But with the go back end, you see that all of the the windows with the window. The window is separated. Right? So the window here's the window. Here's the window. This is the window. See that? This is the window. Okay. The window it just contains all the packets that not yet ACK and already not yet sent. Okay, right? Not yet sent. So yellows and green. Okay, and when we receive ACK, when we receive green, right? When we receive the green, we just move up the window. Okay, right? So basically, it's very it's easier, not very easy. It's easier to implement, like go back end, easier compared to the selective repeat. Okay, right? And but for sure, the go back end, the resource required for us is more because why? When you resend a packet, you need to resend all the packets that have higher order than the current one. Okay, right? So there's a pros and cons of go back end and selective repeat. Okay, right? But actually, right? In practice, go back end is very popular because it's just easier. Okay, and in case of the your network is so-called not really that unreliable, and you can you can use the go back end more convenient than the selective repeat. Right? Okay, so that's it. Okay, so that's it. That is the we're talking about the selective repeat and go back end. Okay, right. We will take a few minute break. Okay, let's say just few minute break, and then when we come back, okay, I believe that we have the I already asked. Let me double check the presentation pipeline. Okay, right. Presentation pipeline for this class. Okay, right. Today we have the Quân and Hoàng Duy, right? Hello, Quân. Are you prepared, Quân? Did you prepare your are you well prepared or did you prepare for the presentation, Quân? I mentioned to you last week, right? Hello, Quân, Trần Quân, and Hoàng Duy. Hoàng Duy is not here. Rồi. Hoàng Duy is here. Sorry. Okay, right. Sorry.
Yeah.
Duy is here. Right. Did you prepare for the presentation, Duy?
Our group prepared.
I cannot hear you, Duy. It's a little bit.
Our group was prepared.
Okay, right. So we're gonna take about 10-minute break, okay, and then when we come back, you will present. You will present, Duy.
Okay. Yes.
Okay, right. Thank you. Right. So let's take 10-minute break. Okay. Bye. All right. Hello. Welcome back. Huh? Okay. Right. So I finished present to you about the two very important mechanics in reliable data transfer. Okay. It's going to be used in TCP protocol. Huh? Right. The selective repeat and the go back end. Right. We're going to learn the detail about TCP probably in next lectures. Huh? Right. For now, I will let's see next group, Duy and Quân. They will present about you know, like one mechanics from TCP. That is the congestion control algorithm. Right. Okay. Right. But before we do that, all right, I believe that next group will be Hồng, Ân, and Thanh Trúc. Right. Okay, right. So Ân and Thanh Trúc, you guys, can you guys prepare for next week's presentation? Right, the evolution of the Ethernet. Hello, Ân and Trúc.
Yes, teacher.
Okay, right. So Trúc as well, huh?
Yes.
And Trúc, right? Okay. Okay, so that's it. So that is all assignment for the next week. Okay, and the week after that, Minh Hoàng and after, sorry. No, we don't have any group to volunteer for Wi-Fi. Okay, right. So we skip that one. All right. So next week will be Minh Hoàng, right? And Triệu Mẫn and Trọng Tấn. Right? Am I missing someone? Am I missing someone? Tôi có thiếu ai không? Am I missing someone? Because we only have like a group here, right? And we only have like 15 person. Okay? So not for sure. If anyone missing still do not have any topics, please tell me. Yes, right. Right. So now I would like to invite Duy, okay, and Quân, okay, right. And I'm gonna stop sharing the screen, my screen, right? So let you guys to have it. Okay. All right. Duy and Quân. Right. Hello. Chạy đâu rồi? Duy, Quân quay lại chưa?
Dạ rồi thầy, đợi bạn Quân xem màn hình cái thầy.
Okay. Rồi, tôi bắt đầu chưa? Thấy xem màn hình này nè.
Máy bạn Quân đang lỗi nè, thầy đợi xíu nữa.
Mấy cái này là Google mà, em lên Google cũng được mà. Em kêu bạn share cho em.
activity increase. Multiplicative increase the case assumption is that drop bucket and the real resolution timeout are due to congestion as the routage or with multiplicative degree TCP risk to a timeout by having CWND, also CWND is defined in by the lecturers often discuss congestion control in terms of bucket, or more formally in MSS equal maximum send size. CMND is not allowed below the size of the single bucket. Next to AIMD, it has been so that AIMD is necessary condition for the TCP congestion control to be stable, because the symbol CC mentions in English somehow that's called restaurant mission. It's important that hosts have an accrued timeout. Merging timeout is set a function of array RTT and standard division of RTT. However, TCP hosts only sample round trip time once per RTT using cross gray clock. Figure type TCP Bluetooth button. Slow start, linear at the increase take too long to ramp up a new TCP connection from cold start, beginning with TCP threshold. The slow start merging was asked to revive an integral exponential increase in the size of C and D. Remember, merging by stack reset stack. Moreover, slow stack is slow than sending a full at the static window was of the bucket on S1. The should start with C cap and D equal 1 every time an ACK right CF and D is incrementic. CF and D is effectively double per RTT able to slow start situation as very beginning connection close start when the connection gets waiting for timeout to occur. This figure slow start. However, in the second case, the suit has more information. The current value of CP and D can be say as congestion. So the this is also known as slow start threshold. Figure behavior of TCP congestion control. Next, please, Duy, present.
Okay. Fast retransmit course timeouts remain a problem, and fast retransmit was added with TCP Tahoe since the receiver responds every time a packet arrives. This implies the sender will see duplicate arcs. Basic idea use duplicates arc to signal lost packet. Fast retransmit using receive of 3 duplicate arc, the TCP sender retransmit the lost packet. Next, generally, fast retransmit eliminates about half the cost frame timeouts. This yields roughly a 20% improvement in throughput. Note, fast retransmit does not eliminate all the timeouts due to small window size at the source. And this is the figure about the fast retransmit. Fast retransmit and based on 3 duplicate arc. And the next one is the figure about the TCP fast retransmit trace. And the last one is the TCP congestion control. This is how the TCP congestion control work. Based on the every unit congestion window to every unit round trip time. And let me explain clearly to you guys about this graph. Next slide. First, fast recovery was added with TCP Reno. Basic idea: when fast retransmit detect 3 duplicate arcs, start the recovery rosette from congestion avoidance region and use arc in the pipe to paste the sending of packet. After fast retransmit, have a CWND and comments recovery from this point using linear additive increase gram balance over arc in pipe. We move to modify low star. With fast recovery, slow star only occur at cold star after a cold spring timeout. This is the difference between TCP Tahoe and TCP Reno. So here's again the TCP congestion control, how it works. And in this slide is a fast recovery would cause a change here. Let's move on the adaptive retransmission. RTT knows at round trip time between a pair of hosts on the internet. So how to set the timer value? The timer value is set as a function of the expected RTT consequence of a bad choice. So here's original algorithm. Keep a running average of RTT and compute timeout as a function of this RTT. It send packet and keep timestamp decided by Tx, and when arc arrive, record timestamp decided by Ta. So we have the formula sample RTT is equal to Ta minus Tx. Uh, uh, Next is the formula about how to compute a weighted average. Estimated RTT is equal to alpha multiplied by estimated RTT plus 1 minus alpha parenthesis multiplied by sample RTT, and the final how to compute original TCP spec alpha in range from 0.8 to 0.9. The timer will be equal to 2 by thrice estimated RTT. So next is Kalm-Petri algorithm, an obvious flaw in the original algorithm. Whenever there is a retransmission, it is impossible to know whether to associate the arch with the original packet or the retransmit packet. So here is the figure 3 about associating the arc. So the finally algorithm is Jefferson and Carroll. The problem with the original algorithm is that it did not take into the account the variance of sample RTT. The difference is equal to sample RTT minus estimated RTT, and estimated RTT is equal to estimated RTT plus 3 plus delta multiplied by difference, and the deviation will be equal to delta multiplied by difference minus deviation, where the delta is a fraction between 0 and 1. And the last formula is when we want to compute the timer using both the mean and variance of RTT, the timer will be equal to mu multiplied by estimated RTT plus 3 multiplied by deviation, where based on experience mu equal to 1 and 3 equal to 4. See our lesson today for today. Thank you guys for listening.
Right, so just be quick again, right? So first thing first, it's just not a like kind of a presentation to you guys, because you simply I believe that you just compose this slide from the internet sources. Okay, it's okay, okay, but please, you need to understand what you are presenting. Yeah, right? And do not read the slide. Okay, it's not appropriate way to present. Okay, yeah, okay, right. So do not read the